Okay, so let's go ahead and get started. So last left off, I told you I was going to pick up right with steady state kinetics. This is an ideal scenario right here. A steady state kinetics is also called Michaelis-Menten kinetics, named after the scientists that proposed it or derived it, I should say. And the hallmark of it, and I'll explain where it all comes from in just a moment, but the hallmark of it is the fact that you get these pseudo first order kinetics at low concentration of substrate. This is rate, initial velocity. You get, at really low concentration of substrate, you get these pseudo first order rate kinetics. It's dependent upon only on the substrate concentration and not on the enzyme concentration. And then as you get to really high concentration of substrate, that means that all of the enzyme binding sites are bound, and so therefore it no longer is dependent upon either substrate or enzyme concentration. It's just on what's called the Vmax, the maximum velocity. Okay, it's that asymptotically, literally from calculus, it's the asymptote that's approaching. Okay, so now I'm going to get. I really wish that this had a black background, and I don't know how to change it. Let's see if I can find a way to. Okay. So this is our reaction. Like, we're going to do one that's relatively simple. Remember, we have enzyme. First has to bind substrate. We're assuming that it's reversible binding to make this ES complex, which sometimes is also called the Michaelis complex, named after Michaelis-Menten kinetics, which then does the chemistry, whatever, to become EP, which then dissociates to form enzyme plus product. Nothing earth-shattering thus far. Hopefully. Each of those is going to be, the D, the S, the ES, the EP, and the P are all going to be a different color, or I'm going to try to do different colors to make it more obvious. Okay, so what's going to happen is, let's just start. I'm going to leave enzyme by itself in white. This is white, right? That's this color. That's white, isn't it? Okay. All right. So at time 0, we've got some set concentration. It doesn't really matter. Some set concentration of enzyme. It could be. This is free enzyme. It's not bound to anything. Okay. It could be higher than that. It could be lower than that. It doesn't really matter. You just pick a point on it. What's going to happen as time goes by? Is the concentration of free enzyme going to increase or decrease when it goes to bind substrate? Decreases. And it doesn't really matter so much like what the rate is right here. And at some point in time, you'll never get all the way to 0. Because, the odds are, but it doesn't really matter so much where you put the head. But at some point in time, it's going to be finished making product, right? You're going to get your enzyme back. And in theory, it should come back up to where you started. This is supposed to, so roughly right here, if you had enough time, it would come back up. Roughly where it started. So there's nothing, like I said, nothing earth-shattering. Once again, this is the concentration of free enzyme. Now, I'm going to do substrate, and I'm going to make substrate this color. At time 0, and it doesn't really matter so much for our intents and purposes where we started off with, but just to make it really obvious, I'm going to put it up here. It starts off at some point in the beginning. In the beginning. Set by people free. No. So we have so much substrate. I'm deliberately not putting it at the exact same concentration of enzyme just because that way you can tell one from the other. What's going to happen to the concentration of substrate? Is it going to go increase or is it going to go down? It's going to go down, right? It's going to be bound by enzyme. It may go faster, it may go slower. But unlike enzyme, you don't get it back typically, right? It's in theory, it should go. It may not go all the way to 0, That's just to show you that it's going down. Okay. I was thinking of like Johnny Cash. All right, now I'm going to do ES. And ES is in this color. At time 0, what is the concentration of ES? 0. Okay. Is it going to go up or is it going to go down? It's going to go up. So it's going to go up. It may take a little bit of time for it to really catch on, but it's going to go up. At some point in time, it's going to flatten out. Like you've got as much ES, it's going to be forming. And then what's going to happen to the concentration of it? At some point in time, it's going to go down and start to approach 0 as well. So once again, that right there was the concentration of ES. Right? Because eventually you're going to be converting it all to product, in theory at least. So it goes up, and it doesn't really matter where you put this, the maximum at. Okay, so I'm just trying to make it to where we've got a lot of space so we can see things. Likewise, we're going to do the same thing for EP. Let me change the color. EP will be this color. At time 0, what is the concentration of EP? 0. So it's going to go up too. In the beginning, is it going to go up as fast or slower than ES? Slower. It takes a little bit longer to get it. But likewise, it's going to go up at some point. I'm going to put it bigger, but it may be smaller than ES. That's not so important. But it's going to plateau as well. Okay, all the enzyme is bound that you can possibly get bound. So you're going to get, and then it's also going to go down. Will it go down sooner or later than the ES in theory? Later. It takes a little bit later, and then it's going to go down too. And it too, in theory, should approach 0. Okay.
Will it not be the same concentration as ES?
No, not necessarily. Because it depends upon, well, you can see it because it says biochemistry lecture. 1 minute. Let me see if I can. And I know where we're at. Okay, it depends. It's always it may be, but not necessarily, because it depends upon this equilibrium constant. If one of these smaller smaller kinetic rate constants is different than the other, then it won't be the same. Okay, so it just depends on the nature of that enzyme. Maybe I'm just exaggerating it so that way we can clearly see one or the other. In reality, I doubt that there are orders of magnitude between them. But okay, and then finally we have free product. Okay, in that color. And at time 0, how much product do we have? 0. And is it going to be faster or slower than EP? It'll be slow. It's going to take a little bit longer to come along for you to be able to see it, right? And in theory, whoops, this is not very good. But in theory, it's going to go up. And it's not going to go back down unless you're doing the reverse reaction. Okay, that's supposed to be a nice little hyperbolic function, but it isn't. You get the idea. Okay, hopefully. It goes up because you're making more product, substrate's going down. Then we have what's called the enzyme down intermediates, ES and EP. And then E is some category else to itself because you have to get your enzyme back, otherwise it's not an enzyme, it's not a catalyst would be reacting. However, if you notice, if we look at just the enzyme intermediates, the ES and the EP, there is this region of time. This is going to be an approximate. Where their concentration is steady. You know what I'm saying? It's a flat line. Okay? that region, those conditions right there is called steady state. That's where it comes from. And it's because the enzyme-bound intermediates, this one, the EP and the ES, it's flat. In calculus, of course, this is where calculus comes into play. The way that they say flat, does anyone remember how they say flat? Calculus. The derivative is equal to 0. And so that's, and technically, mathematically, that is true. It's, you know, that's why, but why make it, and we'll call it X, concentration of whatever with respect to time is equal to 0. But literally, it means it's a flat line. Okay, and so there is some practice involved, but we try to keep it at a minimum, not too difficult. The reason why, and by the way, the region that's before the steady state, does anyone know what this period of time is called that's before? It's called pre-steady state. Because in kinetics, there are 3 major fields of kinetics, if you want to think of it that way. There's steady state, which is also called Michaelis-Menten, which is what your book will focus on, which is the easiest to do and to understand mathematically. There's the pre-steady state, which is this region before, and I'll talk a little bit about it. And then they don't talk about post-steady state at all. But then there's one called single turnover, which, just in case for your papers, if you read something called single turnover, it's where you use so much enzyme you only see the chemical step or the rate limiting step of the reaction, and because it literally can only happen one time. Single turnover. You see whatever the slow step is, that's the one that you measure. It tells you the least amount of information. The problem with pre-steady state is if we look at it, its plus is also its minus. You know, its virtue is also its detriment. Is it tells you literally everything that's going on, the rate for every single part. But there's so much information there that it's mathematically, it's really hard to separate it out. And so unless you can manipulate some way to be able to tell each one of these separate from the other, like you have to be able to know what color based or whatever. If like here we can tell the difference in the color, so we can actually say, okay, we're going to measure the rate of what is that, yellow, and we can do that. In reality, especially in vivo, it's almost impossible to do, right? Or you have to really know every step of the mechanism. You have to know for sure all of the steps that's involved in order to be able to isolate, say, we're only looking at the yellow. And the yellow is this step, it matches up to that part. For a steady state, all of the intermediates that are bound to enzyme, it equals 0. Okay, so it makes the math much more simple, but it doesn't tell you quite as much information. But it does tell you information. And so that's why the books almost always, especially in beginning level biochemistry classes, which this is, they almost focus primarily on steady state and kids mentioned kinetics. But yeah, mathematically it's much simpler. Okay, so we say all of that. That is just so cool. So some other things to keep in mind. Steady state, once again, I've been saying this, but I'm going to just write it out specifically. Steady state kinetics equals, or is the same thing as saying Michaelis-Menten kinetics. And by the way that this is set up, the way that you would experimentally do this is the concentration, this is true for when the concentration of enzyme is much, much less than the concentration of substrate. And in vivo, many times that's true. A lot of times your body only makes a small amount of the enzyme or something, and there's a lot more of the substrate around. Okay. Because otherwise, and this is the reason why remember if you go back to where we wrote out E plus S goes to ES to EP to E plus P. It's right there. I forgot. Read it small. Remember the way that this looks is it looks pseudo first order. In reality, it's a second order reaction. E and S kind of got to come together. But what you do is you make substrate concentration so much larger than enzyme concentration that their relative amount of E is unchanged. Okay. It doesn't matter, it's minuscule. All right, so what does this mean? Where do we go from here? Just a second. Normally, I take one whole class period to do nothing but like 2 slides on this, where we go step by step and we derive it, and we can see where what's called the Michaelis-Menten equation comes from. Because this, unfortunately, I don't know if we have time to do that this year, but I'm going to go a little faster than normal. But the Michaelis-Menten equation is one that you need to know. Okay, so it's not going to be given to you for the exam. This is a little heads up. All right. I'm telling you, I just really don't like the book. I don't like the way the book. I haven't looked in the 7th edition, but at least through edition 6, and I doubt that they changed in edition 7, they assume you are much more adept at calculus, or I should say much more at ease with the calculus behind it than what you probably are. Okay? Because even with me reading it, I'm like, what are they talking about now? You know, I have to kind of sit down and think about it. And it just takes a lot longer, so I like to work it out. I try to do it some with the PowerPoints, but even then, I don't think it does it justice. Okay, so let's get started. We're gonna have some fun. All right, so we're going to even simplify this further to make the math as easy as possible. We still have E plus S. Goes to make ES. But what we're going to assume, and this is true many times, there are many enzymes that normally do this in vivo. We're going to assume that the chemistry step is essentially irreversible, because it makes the math much more simple, okay? And that's a good assumption for many instances. So since it's irreversible, we only have one arrow. It goes to make E. And not only that, here, I'm gonna write it. Let me write it, don't write this down. EP, and that its binding is, here, I'll just show you. Because this is the kind of stuff that we've been seeing before. There are 2 assumptions that we're going to be making. One, the chemistry step, the ES to EP is irreversible. And 2 is that substrate dissociation is very fast. Okay. So in doing those 2 assumptions, this simplifies even further. So this becomes, all of this, I'm trying to do a different arrow. That is a really crappy looking arrow. That's supposed to be an arrow, but not a reaction arrow. All of it becomes this right here, E plus S to ES, irreversible, E plus P. Notice there is no EP. Okay. There's a couple reasons behind that. One, like I said, is because product dissociation is so fast, EP doesn't exist for any appreciable time. Second, we're going to be they look at kinetics. Actually, let me just explain this. This is a little background. Which I don't even know if the book even explains it at all, to be honest. I was trying to remember. If we look at the concentration of product as a function of time, of course it's going to start off with 0, right? What's going to happen is it's going to go up, correct? And at some point in time, it's going to peter out because you're going to use up all the substrate. But when we talk about reaction velocity, V or nu, I usually write V. A lot of times people in biochemistry just write a big capital V. How do we measure that? What is velocity? You know the rate law, but not even the rate law, but if we're just talking about the velocity, how do we measure the velocity or the rate of formation of product as a function of time? What is it equal to? It is, I just want to make it even more simple. It is the derivative of this, right? It's just literally the change in product as a function of time, just like velocity in your car. How fast are you going per hour? Okay. Which my wife was going all over the place last night on the way to Orlando. All right, so, okay. But the problem here is it is a derivative, you know, and if it makes you feel more comfortable to write it this way, with a triangle, you know, with a delta, please feel free to do that. But that right there is the same thing as this. I don't know, do they tell you that in calculus? I don't know, in Gen Chem and stuff, a lot of times they put the triangle, this needs to change. Well, the problem with this is what? Does anyone see that? What's the problem if we wanted to do this, measure this velocity? And like I said, I don't think your book tells you this. You just assume that you want to know. What is the derivative of this right here?
Would it be 0? Because it's at the top it's like flat.
At the top it's 0. That's right. But here it's not. So the idea is the derivative is changing. And then in calculus you probably had to plot it and you get these like really freaky lines. Of course, experimentally, if you were here like trying to measure, you know, someone, do a clinical study on someone, you're not going to want to, you know, do you measure here, do you measure there, do you measure there, where do you measure? And so what they do is they do what they call initial velocity. We only we measure initial velocity. So what they do is they only measure it for short periods of time. Here in this very beginning part, so therefore it doesn't really change. It's not 0, it is a number, like you do have a reaction rate, but they only measure initial velocities. Depending on the enzyme that you're working with, sometimes it's, you know, maybe on the order of minutes, sometimes it's only order of a fraction of a second. You know, whenever we're doing it in mitochondria for the electron transport chain, if it's turning over 100,000 times per second, those initial velocities have got to be milliseconds, if not smaller, right? So therefore, I think your book probably just tells you initial velocity. Or it used to. It just didn't explain the reason why. But the reason why is because in reality, the derivative of that line is going to be changing. The velocity changes as time goes on. So we have to have like a common measuring post. Okay, let's get back up there to our equation. All right. So, okay, let me just make that small. Yeah, you can still make it out. E plus S goes to ES to EP. So, under steady state conditions, this must be true. The rate of formation of ES has to equal the rate of breakdown. That's me putting it in like common words. In calculus, they would have said the derivative was equal to 0. There's no change. In order for there to be no change, you have to be making it as fast as you're breaking it, or vice versa. So if you think more calculus-wise, feel free to write DES over DET is equal to DES over DT is equal to 0. I write this. Okay. So now let's write this out. The rate, or if you want to put V, you can, but I'm going to say the rate to form ES is equal to, remember, now we're going to be writing the rate law. Every rate law has what? Every rate law, remember, it has a, someone said I thought, Okay. Okay, so if we look back up here, how do we make ES? This is ES. Do we have, how many ways do we have to make it? Just E plus S. That's why, because we got rid of going backwards. We said it was irreversible. Okay, so therefore, if you remember, I'm going to write back the K's. I don't know if I can write that tiny now. That's K1. This is K minus 1 going backwards, and this is K2. I meant to write that in earlier. So which of the little K's makes ES?
K1.
K1. And so you just write down K1. Okay, and what concentrations does ES formation depend on? Like what goes together to make ES? E and S. And so it's just E times S. And so that's it. Okay. So in a different color, I'm going to do the rate of breakdown. I'm just going to call it the rate to break. ES. All right. So how many ways do we have to break it? Up there. We have ES in the middle. How many ways do we have for it to disappear?
Yes.
Two. You can go either frontwards or backwards. I guess frontwards or backwards. Sorry. You get the idea. Okay, so hopefully. If we go quote unquote forwards, how about forwards instead of frontwards? Forwards, which little k is the forward direction? K2. And what concentration is dependent upon, is K2 dependent upon? ES. Plus, now we gotta go for the backwards direction. Which of the little k's is backwards? K minus 1. And the concentration is dependent upon K minus 1. That's probably the hardest part here to think about it. What's K minus 1 is dependent upon what concentration or concentrations? Just ES. Just ES. But remember, it's going this direction for you guys. And so it's only dependent upon ES going backwards.
Wouldn't it be dependent on, if there's a low amount of E plus S, wouldn't that promote ES going backwards?
No, that's at equilibrium, which we're getting to that. You actually get that. That's with the capital.
Wait, and I thought you said the amount of E was negligible to S.
It is. We're going to prove that. I mean, it is. So, but not for ES.
I'm talking about for the top one, green one.
For the what?
Form ES, isn't E, doesn't matter anymore, it just matters.
Oh wait, no, we're going to leave it here. Because what we're going to find out is this number here, it's negligible with respect to S. S is much larger than E. That becomes important for denominators, not for numerators. Okay, and so, and I mean, I'll get to that in just a moment. Okay. All right, because it's not 0, because otherwise the other thing would come out to 0. But yeah, it's just ES here, not E plus S. It's the same. Because what it is it's just this thing right here. Does that show up the same? Yeah, this thing right here going backwards. So therefore, by definition, at steady state, formation has to equal breakdown. I'm just going to put it in a different color. So that means that K1 E times S has got to equal K2 ES plus K minus 1 ES. And then I think in your book, it goes from this and just tells you this isn't the case mentioned equation. At least it used to. It may have one more step, but it doesn't show you anything else of great import. Like what do you use this for? You know, Yes, it's true. Rate of formation is equal to rate of breakdown. So now let's go back to the original here. Remember, we're doing everything with respect to P, because this was the change of product with respect to time, so how much product you're making. So what, I'm going to call that one big V over here. This is just a little side note. Big V. Once again, you can even call it VI or V initial, what have you. The one that's in that little side graph. It has a rate law as well. Okay. So what is the one way, we only have one way to make product. What little k is associated with it? K2. Okay. And then what's the concentration that's affiliated with K2 to make product? ES. Now the problem that we have here is almost always, I'm sure a handful of exceptions, almost always in vivo, in your body, we don't know what the concentration of ES is. And even in vitro, like if you mix substrate, I have so much substrate, I have no product in the beginning, and so much enzyme, I mix them together, then you make product. We don't know what the middle usually is. You only know the end result and what you started off with. Does that make sense? So we know the total amount of enzyme, usually, and we usually know the substrate, and you can measure product, but we don't know that ES and EP. And so, the total amount of substrate, which usually, what you're going to find out is in the Michaelis-Menten equation, is ET, but a lot of times they just call it E, but it's not free enzyme, because E total, and these are all concentrations, it's just, in case you can't tell, as time goes on, my brackets disappear, but it's free enzyme plus the concentration of ES. Okay. Alrighty. Okay. So what's going to happen here is, let's see, how are we doing on time? Oh my goodness, we're almost out of time. Way down below, I'm going to give you the answer because I have a feeling that we're not going to get all the way through it. V, or V initial, V, the rate. This is the answer. K2 times E times S over Km plus S, which is also equal to what's called V max times S, over Km plus S.
Is that capital K or little k?
This is a capital K. That's very important to note. Okay, the little K2 is a little lowercase k. That's a capital K. That's supposed to be capital K as well. Because it's a thermodynamic constant. Okay, so what we can do here, and I'm hoping to go from here at this point to this point, like I said, your book just tells you, throws it at you. Unless they changed in the 7th edition, which I haven't checked the 7th edition to make sure. But we can go ahead and start to, we can put these terms together. They both have ES in them, right? And likewise, okay, yeah, I'm just going to do that rather than skipping a bunch of steps. Oh, whoops, I didn't mean to do that. So this becomes K1 E times S is equal to ES, whoops, this being E, times K2 plus a K minus 1. Okay, so this enzyme here is free enzyme, remember, not enzyme total, which we don't necessarily know the free enzyme at all points, but we know the total that we started off with. So we can solve for E in terms of ET and ES, which is good because this isn't in terms of ES and this is in terms of ES. Does that make sense? So therefore, over here, in this color, we can say that E, like free enzyme, is equal to the concentration of enzyme total plus ES. Okay, so it's important to know. Okay. Okay, so it's just something to know for just in a moment. We want to get ES by itself. So see, the whole purpose of doing all of this, which your book doesn't tell you, is you've got to solve for ES. So if we stopped right here, we could solve for ES. It would be K1 times E times S divided by these little K's, correct? But we just don't know what that E is. And so therefore we can substitute in for this E, all of this right here, ES and then ET. So I'm just going to put this over here. So it's K1. I'm going to go ahead and put the S right here because that's fine. And then for E, big parentheses, it's ET plus ES.
Would it not be minus ES?
Oh, I'm sorry, yeah. Good. Thank you.
Yeah, I was like,
It's minus. Oh, whoops. And this right here is minus, not plus. And not times. But I don't think it'll let me see, maybe it'll let me erase all that over here. Oh, it does, good. There's like a memory, like a amount of time before it stops. We'll no longer let you go so far back to erase. Now, all of this is equal to this other side. To ES. K2 plus K minus 1. So we've got to get all of the ES's on one side and everything else on the other side. So give everybody a moment to get caught up. Let me see if I can get this to go. Oh, good, it will. Good. Unfortunately, it leaves the little plus, the little minus behind, and I apologize for that, but it won't let me. Let's go over here. I'm just moving this all up. So once again, boy, that is really bad. This K1 times S, parentheses, ET, total enzyme concentration, minus ES, in parentheses, is equal to ES, and then the little K's that are added together. So I'm trying not to skip any steps whatsoever. I'm going to change colors, so that way it's easier for me to tell. I'm doing K1S times ET minus K1S ES is equal to ES. So what we're going to do next, remember we're trying to get all the ES's on one side. So we take this ugly thing here, and we make this one even uglier. So we're going to add this entire term over to the other side, and leave this stays behind. So K1S times ET is equal to everything that was there before. Plus K1S. And that's supposed to be concentration of S. See, I told you I'd lose my brackets as we go along. Times ES. Now we can simplify this since we've got an ES and an ES, which sometimes they wait and they do all this at the end. But I didn't want to before because it gets a pain to write all that out every time. So I'm going to this is all the same. I'm not changing that at all. Is equal to, we factor out an ES. But now this becomes K2 plus K minus 1 plus K1 times, I'll remember to put my bracket back in that time, that. So I told you, it gets ugly. And since we have all these little K's, so we're going to get, it's not a fudge factor, but we're getting close to what you can almost think it's a fudge factor. So to get ES all by itself, what do we need to do? You divide by that, okay? So therefore, we get K1 times S times ET divided by K2 plus K minus 1 plus K1 S. I told you it's not pretty. Okay, and that is equal to ES. Okay. Now I'm just going to show you, just to remind you, actually I may be able to point to it up here. Remember, the ultimate goal is to solve for the initial velocity, which was equal to K2 times ES. Well, we now have ES, but this is scary looking, right? Do you see what I'm saying? It's really weird. Okay, what they like to do here, or what you can do, and this may very well seem counterintuitive to the way that you're used to doing algebra. But we can actually factor out the K1, which you probably had been, you had an algebra teacher, like my algebra teacher in high school, which I'm sure they can no longer do this, or in school, would actually slap our hands, and it wasn't a Catholic school. But if she slapped our hands, we would have done that. But there's a way to do it, okay? It's just not the most intuitive way. Because you have a K1 here and a K1 in this term, but these terms don't have a K1. So if you think back, what it means to factor it out, it means you divide everything by K1. And so as long as you divide these by K1, it's all good. I wanted to say that because I'm going to give you the answer. Okay, so let me move this all up a little bit to give myself a little bit more room. So we're going to divide everything by the K1 over K1, or multiply it by K1 over K1, whatever your inkling is. And so what happens there is that on the top, it's just substrate times enzyme concentration. On the bottom, I'm going to write it a little differently. I'm going to write it as parentheses, K2 plus K minus 1 over K1. See, that's true. When we factor out that K1, that is a true term. So that way, when you multiply everything by K1 over K1, you get this back. Okay, now the one thing that's missing here is plus S. But the reason why we do that, and I don't know if they teach you this in calculus or not, or you probably have forgotten, but we're going to you're trying to get, like, if you think of you probably y is equal to x, what our x is going to be, you want to get it by itself here. If at all possible, this is going to make the shape of a hyperbola. It's hyperbolic hyperbola. It's a hyperbolic function, okay, and that's what we're making. All right, this is the cheat factor that I'm going to talk to you about. This right here, all of this nastiness, all these little k's, these ratio of k's right here, even though those are individual kinetic rate constants, taken together they're an equilibrium constant, a thermodynamic constant. It's a capital K. They give that ratio right there a special name. It's called Michaelis constant, and it's Km. That capital Km. That's where the capital Km came in. And so rather than having to write that out every single time over and over and over again, they just say Km. And in this instance, that Km is equal to K2 plus K minus 1 divided by K1. And it literally means it's just the ratio of all the kinetic rate constants involved right there. Okay. It's not really a fudge factor, but it makes it so much easier to write. So if we rewrite all that, how are we doing time? This becomes, that ES becomes, oh, let me change the color back. That ES becomes this. ES, concentration, is equal to substrate times enzyme, the total enzyme concentration, divided by Km plus substrate. That's a lot prettier looking than what we started off with, right? Now all we have to do is take that one that I just wrote and stick it up there for the initial velocity, and that's Michaelis-Menten. That's where it comes from. So I'm going to try to move all of this up. So before, you can barely see it now, I'm going to do it in this color. We had said that the initial velocity, or V, was equal to K2 times ES. Well, we now have an ES. That ES, so it's going to be initial velocity equal to K2 times substrate times the total enzyme concentration divided by Km plus S. Okay, and so all that they do now is they just, which is the same thing, I'm just going to put it in the traditional format that you see with the book, is that V is equal to K2 times E times S, and this time they just write out E, they don't write E total, but it really is E total over Km plus S. They call this right here, this is special, okay? And on Monday, we're going to pick up with that. They call this little K right here, they call it K-cat. And so therefore, K-cat times E has a special name called V max. Because what it means is this right here, that K2 is the catalytic rate constant. The rate constant for the catalytic step. It's important. The removing step. But since in vivo, in the cell, a lot of times you don't know the exact concentration of enzyme, they just call it V max. You can figure out the maximum velocity. Okay, so that's why if you rewrite V, it's gonna be this. V is equal to V max times S over Km plus S. Your book just the very first step or two, and then it just gives you that, at least up through addition 6. That's where it's going to come from. And we're going to be using a lot of mathematical logic to work with this right here, to see what that means, and why do we do this? How do we do this with respect to enzymes? I'm trying to get that all done, get as much of it done before you turn in your rough drafts, but if you do what we can. Okay.